So, welcome to lesson one in energy resources. And in today's lesson, we're going to be covering four main points. Number one, we're going to be looking at some basic definitions and covering or doing some revision from previous concepts, particularly from chapter two. Secondly, we're going to be reviewing the concept of efficiency using Sankey diagrams. And if you don't know what those are, don't worry, you will soon. And then number three, we will be describing how fossil fuels can be used to generate energy and specifically electricity. And then we'll be doing some maths, okay, using the ideas outlined above. So first I'll be reviewing two definitions that you've definitely come across before, and that's the idea of a renewable and a non-renewable energy source. Now this is to do with fuel and how we make electricity. A renewable energy resource remains undiminished or is replaced through natural processes during our human time frame. That means that as we use it, we are still continuously replacing it. A non-renewable energy resource is one that will be consumed much faster than it is replenished, and that means that it will eventually run out. So here are some examples of each. We have as examples of renewable energy sources, biomass, solar, wind, hydropower, and geothermal. So these are all sources that will eventually produce electricity for us, which we are able to continuously replace. The ones that we're going to look at in detail are solar, hydropower, wind. Those three we'll do some calculations for later on in the chapter. Non-renewable energy sources, basically energy sources that take a long time to replace, millions of years, so definitely not in our lifetime. And these include nuclear, oil, coal, and gas. These are all, or these three in particular, we refer to as fossil fuels: oil, coal, and gas. And you'll learn a little bit how they store energy later. So let's look at efficiency again. It's been a while. Efficiency is the ratio of power out to power in an energy change, or energy out and energy in an energy exchange or change. I'll give you an example. Take this terribly drawn light bulb. The energy in is electrical. The energy out is light. Well, that's not the only energy change, because some of this electrical energy becomes heat. It's lost, right? But we're not interested in that energy that's lost. We're only interested in the energy that's useful. So in this case, we'd be looking at the energy that's changed into light energy. In this case, we would work out our electrical energy as our energy in, and you'd work out the amount of light you get out, multiply it by 100 to get your efficiency. Power is proportional to energy, because energy over time gives you power, right? So if you look at energy as a rate, how much energy do you get per second, then it would make sense that these two would be equivalent, right? So you can use both in the equation. Efficiency rate in mechanical systems are actually pretty poor. If we look at a steam train, 5 to 10% efficient. That means that up to 95% of all the energy that you put into a steam train is lost as heat. Human muscle, 20 to 25, so we're pretty rubbish as well. And your average car, less than 25%. So that means that 75% of the money you are putting in for fuel costs are actually just basically thrown out the window. Electric engines are actually a little bit more efficient. This is an electric motor, which is not exactly an electric engine, but we are becoming more efficient as the technology improves. I just wish those cars were cheaper. And now comes Sankey diagrams. Now, drawing Sankey diagrams is a very, very important skill. A Sankey diagram represents three things. The first one is the energy input, right? How much energy is putting into your object, your mechanical system. Secondly, how much energy is coming out that is useful. So yeah, this totally ties in with efficiency. And then thirdly, you're going to show wasted or unwanted energy. So it's a little bit like efficiency, but we're actually quantifying all three things, not just two of them. Now, how do we draw them? Well, the first thing we need to do is to draw the useful energy as a straight line. That wasn't very straight, but I think you get the picture. We start off with the energy input at one side of the arrow, and at the tip of our arrow, we represent the useful energy. The wasted energy we always show as coming off to the side. Now in this picture, it's going down, but it could just as easily be pointing upwards. The important thing is that it's coming off the arrow, either up or down. So the second thing is, what do we do with wasted energy? We either go up or down, but we veer off the arrow. And then thirdly, how do we quantify it? How do we show the numbers? We show the numbers by using scale diagrams. You would use the size of your arrows to quantify this, the amount of energy that's being used. So your scale diagram here, the number of squares or the length, would quantify the amount of energy you're using. The same with the amount of energy that's useful and the amount that's wasted. So I'll give you an example. Say, for example, I have here 100 joules of electrical energy coming into a light bulb. Then I would draw here an arrow, which is maybe 1 centimeter. 1 centimeter or 10 centimeters, it doesn't really matter as long as it's all to scale. And that would then mean, let's say, for example, that the useful energy, let's just assume it's 10% efficient, right? So 10% comes out here, and I would need to represent it with a scale diagram. So 10% of 1 centimeter right, would be 0.1 centimeter. So I would then show that that arrow's thickness represents the correct percentage by making sure it's to scale. And then down here, well, if 10% of that original 100 joules is electrical energy, then that means that 90%, which is crazy, 90% is left over as wasted heat. And then I would show that as 0.9 centimeters. Okay. Now, before we move on, I'm just going to identify a very important term here, which is degraded energy. Degraded energy is another way of describing wasted or wanted or unwanted energy. Okay, so it's the correct terminology for wasted or unwanted energy. So please make a note of it. It's fundamental. Here's a few more examples. Okay, so here you have that light bulb again, and it's exactly as I described it before. Okay, and this is how we would draw it. And a quick exercise here. So this is for a car. This particular car is 30% efficient, and you can see 30 kilojoules over here is the amount of energy out. Energy out. And this is your energy in, 100 kilojoules. So how do we work out the efficiency of the car? We would divide the energy out by the energy in times 100, and that would give us our 30%, which is quite good for a car. Sankey diagrams can get pretty complicated, especially if you start considering an entire country, which is this picture. This is the energy diagram for the US. It's absurd, but it gives you an idea of where the energy is going and where it comes from. So we have here our fossil fuels, here we have our renewables, and so therefore you can pretty much draw a Sankey diagram for any situation or any exchange of energy, regardless of how complex it is. Time for you guys to stop listening and to actually do some work. I would like you to do questions number 9 and 10. Don't bother with the rest, just do those 2 and check my answers on Classroom, please. Do not come back until they're done. I hope you enjoyed those exercises, and now we're going to move on to something else. We're going to look at how electricity is generated, right? So here we have a list of non-renewable fuels: coal, petrol, and oil. And there's one missing. Do you know which one? Did you guess? Yes, gas. I'm going to pretend I did that on purpose. Of course I didn't. I forgot to add it on. So here we go. Gas. Those are your fossil fuels. Petrol is actually the same as oil in the sense that it comes from the same source, but it's processed. So these two actually count as one. But coal, oil, and gas are your 3 main fossil fuels. I apologize in advance if you hear the odd squeaks every now and then. I have a really annoying cat, which is normally silent until I start recording, and then suddenly it becomes really vocal. So it's not me that's squeaking, it's my cat, and I can't get rid of it because it keeps sneaking in. So, okay, let's talk about some more definitions. We have primary and secondary energy sources. So these are vital to understanding the concept of a fuel, right? Primary energy sources are basically energy sources such as coal, wind, oil, gas, water, which you can use them directly, right? So if you think about it, coal, you can stick that in a stove and make heat, for example. It's quite useful direct. You don't have to do anything to it. Wind, you can use winds for windmills and use that to grind corn, etc. And that's usually how things were done before. Oil, you can burn it to get heat. Gas, you can burn it to get heat. Water is actually a really good source of mechanical energy and used to be used to grind grain, etc., and to run mills and things like that. So water is another good primary energy source. And these are useful when we consider the alternative, which is a secondary energy source. So what I mean by useful is it's a useful term to separate the two. A secondary energy source is an energy such as electricity, right? Electricity is the main example of a secondary energy source. And basically, it's amazing how reliant we are on secondary energy sources. Now, the problem with secondary energy sources is they involve some level of processing, and those processes are inefficient, right? So as a species, we are now very reliant on secondary energy sources, which are very inefficient, and so we waste a lot of energy just trying to make it happen. Hydrogen is another one that's been thrown in there. It's a good example because you do have to process chemicals, or process your raw products in order to extract the hydrogen, which can be used as a fuel. Anyway, the idea of a secondary energy source is that you have to do something to get it in the first place. And two more definitions, which are specific to fuels themselves. How do we describe how much energy a fuel can give you when you do use it for some kind of process? Well, we have two terms to describe the fuel's properties. One is specific energy, and this is the energy transferred from unit per unit mass. So how much energy does a kilogram of your fuel have? And then you have energy density, which is pretty much the same thing. It's the energy transferred from unit volume, right? So it's how much energy you have per unit volume. So if I have if I need to supply an amount of energy, I can use these two values to work out how much I need, how much mass I need of my fuel, but also how much space it's going to take up, which is important for shipping, etc. But we'll give you some concrete examples in a bit. Anyway, write these two down. Importantly, write these down because we're going to be doing lots of maths with these. Here are some example values, and it's quite impressive, really. If you look at, for example, nuclear fuel. Nuclear fuel has a specific energy. Well, it's ridiculous. I'm not even going to say these numbers. They're too big. We're talking megajoules per kilogram, right? So the amount of energy that's available in just 1 kilogram of uranium is bonkers. And nuclear fusion, of course, this is the binding together of hydrogen nuclei. This only happens in the sun. Like, we don't have access to this as fuel as of yet, which is a shame because it would solve a lot of problems. This is what we have access to. This is uranium. Hydrogen, highly flammable, but again, good source. But let's have a look at our fossil fuels here. We're looking at natural gas, 55, gasoline, 46, crude oil, 46, etc., etc., coal, 28, wood. So these actually are quite decent values of specific energy. And when we compare them to something like water at a height of 100 meters, now this is your hydroelectric, right? That's a pathetic amount. That's much, much, much lower. So although we always look at advantages of renewables, right? Basically, the advantage of non-renewables is that their specific energy is so much higher. And that's very, very important. That's why we're still using them. So I won't keep you in suspense any longer. How do we make electricity? Well, basically, you do need a couple of things. The first one is you need something that will move, a source of kinetic energy, and specifically something that will spin, right? And then the second thing you'll need is a generator. Those of you who've done topic 11 should remember what a generator is. Generator is a magic object with magnets in it that when you move a conductor inside it, usually spinning, right, you generate a current in the wires. We'll have a look at that in a second. So if you have something that will spin for you and you have a generator, then you'll get electricity being made, and then you just need a network of supply. So these are your transformers and your national grid system. Again, that's topic 11 stuff. And what is our source of kinetic energy? Well, our source of kinetic energy can either be fossil fuel based, right? Could be a bunch of fossil fuels burning, and I'll show you how that's relevant to kinetic energy in a minute. You can have nuclear fuel, again, a bit weird because that's not moving, is it? But we'll figure that out in a second. Then you've got wind turbines. It's a little bit easier to see. These spin, right? So spinning turbines, these over here, they're spinning, right? They give you your spinning thing that you need for your dynamo or your generator. And then you've got hydroelectric. Hydroelectrics, how do they spin? They fall, don't they? It's just water falling. Well, we'll have a look at that in a minute. And tidal. Now, it doesn't really spin, but that does move up and down. Okay, so all of these are your source of motion. So I'll tell you now how these make things move. So what's so fancy about fossil fuels? Well, fossil fuels store chemical energy, and they release that energy through the process of combustion. So these chemicals, or rather hydrocarbons, which is their proper name, they release energy through combustion, and then that energy is very useful. Because what that energy does is it heats huge amounts of water, right, in the boiler. So you've got water here, which becomes steam. Now, water doesn't move either. Hang on, what's the moving thing? Well, the water heats up to make steam, and the steam does move. It's placed under some conditions where it's forced through the pipes because it's expanding, because the gas gets hot. If you remember that from topic 3, gases, when they get hot, they expand, they take up more space. This is because their internal energy has increased, right? Internal energy has increased, and then they flow through the pipes and they're forced through into the turbine room and they turn the turbine. So there's your motion, right? The thing that's moving is the steam, and the steam moves because it's gaining heat from the burning of the fossil fuels. This is quick review, and for those of you in standard level, I think it's just one of you. But anyway, if you go back to the idea of the motor, the motor was magnets and a coil, and what you did with a motor is you used current to spin the coil, right? So in a generator, the opposite happens. You basically move your coil around like that. You make it spin, and because it's spinning inside a magnetic field, current is forced through the wires, right? So that spinning is what gives you electricity. These generators are absolutely huge. This is just one of them, okay? And this is how big they are compared to this man. Now, not only do you need to know the processes involved, which I've outlined, you also need to be aware of the Sankey diagram. Okay, it's very common. And your Sankey diagram will show basically your beginning, which is the chemical energy, your source, this is your energy in, and then you would have energy losses, obviously, in the hot steam, okay, and the exhaust fumes. Basically, the entire boiler room gets hot. You're wasting loads and loads and loads of energy. The steam as well, and this is interesting, is worth considering. Your steam, so you're heating up the water, which makes steam, and then the steam goes through the steam turbine, spins the generator here, and then cools down, basically loses all its energy. And as it loses its energy, it condenses, right? It comes down here. And it's actually forced to condense and to go down to a much, much lower temperature. Because interestingly enough, the lower the temperature down here, the colder the water is down here, the more heat it can absorb when it goes back into the boiler room. Basically, you need to try and make this difference in temperature as big as possible. So it's really, really, really hot here. Then it can use that extra energy to spin the turbines, and then it gets cold down here. Okay, and it's constantly. Now, what's happening? And one of the consequences of this, on the one hand, great, because if you have a large temperature, then you're going to be able to turn the turbines a lot. But the downside is you also have a lot of wasted energy, right? All of this heat is lost. And that's shown in your Sankey diagram here, okay, as energy comes off. So what we've got in our Sankey diagram is the chemical energy coming in, the electrical energy coming out, right? Electricity. And then you could have kinetic energy in the middle showing that energy change. Basically, you would show an energy change for each stage. The first time in the boiler room, the second time in the turbines, and then thirdly in your generator. So it's worth making a note of this Sankey diagram. I would like you to take some time now to watch a couple of videos. I'd like you to watch this one on fossil fuels and the next one showing you an actual power station. So stop what you're doing, go get a cup of tea or whatever, and watch the next two videos. They're both on Google Classroom, by the way. So you just have to switch this off, go back to Google Classroom, and find the two videos that are set up for you. Okay, so now it's time for some math. Some of you may love this and some of you might hate it, but let's just see if we can get through it in any case. Let me talk you through the first exercise. Most of the questions in this section are kind of based around the efficiency equation, right? So I'll just review that for you. And here it is, energy out over energy in times 100 equals efficiency. So now let's read the question, see what it's got in store for us. We have coal with a specific energy of 32.5 megajoules per kilogram, right? So that's how much energy is available in every kilogram. Now, if a city has a coal-fired power plant that needs 30 megawatts of power with an efficiency of 25, how many kilograms of coal are needed daily? Now, it's playing with a lot of things. The first thing is it's only giving you one energy, and you don't know yet if it's the energy out or the energy in. It's also talking about daily needs when we all know full well that megawatts are per second, right? So these are all things that you might want to think about before you start. Now, what kind of energy are we given? It says that the power plant needs to produce 30 megawatts. So it doesn't matter how much you put in, the amount that you get out definitely has to be 30, which means that you're going to have to put in an awful lot more. You can use the 25% here to work that out. Okay. Once you've done that, what you've worked out is the energy in per second, because this is watts, right? So what you would then do is to work out the amount of energy that you need in a day, right? And you would then use your value for coal's specific energy to work that out. Do it now. Do it now. Don't take a sneaky peek at the answers until you've tried it. And here we go. You've got your value, 120 megawatts, which is ridiculous. 120 megawatts, that's how much energy you need per second. All right. You multiply it by 24 times 60 times 60 to give you how much you need in a day, right? And then you just use your, you just need your fuel, megajoules per kilogram, to work out the amount of mass you need. Okay, now try all the other questions in 8.1.1 My answers are also on Classroom. Send me a quick email if you want me to make a little video so you can do one of the questions, or if you need extra guidance, or if you just need a chat. Send me an email. See you in a bit.